Hello everyone. Let us continue the second part of today's class. Okay, in the first part of today's class, we have set to here. Okay, explicitly a strict preorder on P is a homogeneous binary relation smaller than or less than on P that satisfies the following conditions. Okay, first, irreflexivity or anti-reflexivity. Not A is smaller than A for all A is in P. That is, A is smaller than A is false for all A in P and 2. Transitivity. If A is smaller than B and B is smaller than C, then A is smaller than C for all A, B, C in P. Okay. A binary relation is a strict preorder if and only if it is a strict partial order. Okay, we will introduce what is a strict partial order later. Oh, sorry, we have introduced it, a strict partial order, on page 46. Okay. So let us go back to the previous page. Okay, here, by definition, a strict partial order is an asymmetric strict preorder, where smaller than is called asymmetric if A smaller than P implies not B smaller than A for all AB. Okay. Conversely, every strict preorder is a strict partial order because every transitive irreflexive relation is necessarily asymmetric. Okay, we have talked about it earlier in the first part of today's class. Excuse me. Okay, although they are equivalent, the term strict partial order is typically preferred over strict preorder, and readers are referred to strict partial orders. Okay, you can see this. Okay, click on it and the PDF file will jump to strict partial order. Okay, let us go back to Okay, let us go back to the previous place. Okay, let me see. Strict partial order. Oh, we have many strict partial order here. Okay, let us see. Okay, here. Okay. For details about such relations, in contrast to strict preorders, there are many non-strict preorders that are not non-strict partial orders. Okay, let us see an interesting example. Okay, please see figure 22. Okay, let us see figure 22. Okay, I need to make this figure smaller. Okay, figure 22 is a hazy diagram. Okay, I do not intend to introduce what is the hazy diagram. Okay, because it will spend more time, too much time. Okay, of the pre-order xry defined by x slash 4 is smaller than or equal to y double slash 4 on the real numbers. Okay, due to the cycles, R is not anti-symmetric. Okay, let us see. Okay, 0, 1, 2, 3. Okay, and back to 0. Okay, so 0, 1, 2, 3 form cycles. And 4, 5, 6, 7 is another cycles. And 8, 9, 10, 11 is another cycle. And 12, 13, 14, 15, 12 is another cycle. And 16, 17, 18, 19 is another cycle. Okay, and so on. Okay, so due to the cycles, R is not anti-symmetric. Okay, do you remember what is anti-symmetric? Okay, let us search for the anti-symmetric. Okay, so I need to delete this. Okay, so what is anti-symmetric? It means if A is smaller than or equal to B, and B is smaller than or equal to A, then A is equal to B. Okay, of course. Okay, let us go back to the anti-symmetric. Okay, here. Okay, because xry is defined by x double slash 4, which is smaller than or equal to y double slash 4. Okay, I think we need to define what is the x double slash 4. Okay. Okay, let us go to, let me see, go to the example. Okay. Okay, by x double slash 4 is meant the greatest integer that is not less than x divided by 4. Okay, do you understand? Okay, let us see again. X double slash 4 is the greatest integer that is not less than x divided by 4. Okay, thus 1 double slash 4 is 0. Okay, do you know why? Okay, because 1 double slash 4 okay, is the greatest integer that is not less than x divided by 4. Okay, so 1 double slash 4 is the greatest integer that is not less than 1. Okay, divided by 4. Okay, so not less than 1. Okay, means it is greater than 1. Okay, thus 1 double slash 4 is 0. Okay, which is certainly less than or equal to 0. Okay, 0 is less than or equal to 0, of course, which is itself the same as 0 double slash 4. Okay. Okay, so back to this figure. Okay, so we know that, okay, 0, 1, 2, 3 are equal to each other. Okay, so because 0, 1, 2, 3 double slash 4 are all equal to 0. Okay, so you can see that you can think as that they are in the same class, okay, or in the same cycle. Okay. Okay, if all numbers in a cycle are considered equivalent, okay, as we said, all numbers in a cycle are considered equivalent. Okay, for example, 0, 1, 2, 3 are equivalent. A partial even linear order is obtained. Okay, so we have obtained a partial order. Okay, or even linear order. So what is a partial order? Okay, let us review it. Okay, partial order. Okay, let me search for the partial order. Okay, here. Okay, partial order is problem 19, which we have explained the solution in the first part of today's class. Okay, so let us go to figure 22. Okay, here. Okay, so next, problem 24. What is a topological vector space? Okay, why do we need to know what is a topological vector space? Okay, let us search it. Topological vector space. Okay. Oh, it is strange. We should have another topological vector space before this one. Okay, let us go back to page 1 and search again. Oh, it is strange. Okay, let us search for TVS. Okay, topological vector space. Okay, TVS. Because it is in the solution to problem 13. What is a locally convex space? Okay, so we need to know it. Okay, let us go to TVS. Okay. Okay, so here. Okay, so problem 24. What is a topological vector space? Let us see the solution. First, let us see the definition of a topological vector space. Okay, a topological vector space, abbreviated TVS, X is a vector space. Okay, I think you already know what is a vector space. Okay, because you have taken the course linear algebra. Okay, so if you forget what is a vector space, please review the course. Review the textbook of the linear algebra. Over a topological field K, okay, we will introduce what is a topological field later. Okay, most often the real or complex numbers with their standard topologies. Okay. Oh, excuse me. That is endowed with a topology. Okay, we will introduce what is a topology later. Such that vector addition, okay, dot plus dot, okay, which is from x times x to x. Okay, here times x times x means the Cartesian product of x and x. Okay, so you can see the addition as a function. Okay, and the domain of the function is x times x, and the range of the function is x. Okay, and the scalar multiplication dot, okay, k times x, okay, maps to x, okay, where this times also denotes the Cartesian product, are continuous function. Okay, I think you have already learned what is a continuous function in the course calculus. Okay, if you forget what is a continuous function, please refer to the textbook of the course calculus. Okay, where the domains of these functions are endowed with product topologies. Okay, we will introduce what is a product topology later. Okay, such a topology is called a vector topology or a TVS topology on X. Okay, every topological vector space is also a commutative topological group under addition. Okay, we will introduce what is a topological group later. Okay, next, problem 25. What is a topological field? Okay, solution. A refinement of the notion of a field, okay, is a topological field, okay, in which the set, okay, by the way, we have introduced what is a field. Okay, let me search the field for you. Okay, field. Okay, we have introduced what is a field in the solution to problem 15. Okay, if you forget it, please review the solution to problem 15. Okay, let us go back to the topological field. Field. Okay. So, in which the set F is a topological space. Okay, we will introduce what is a topological space later, such that all operations of the field, okay, addition, multiplication, the maps A to negative A and A to the power of negative 1. Okay, we know that the negative A is called the additive identity of A, and A to the power of negative 1 is called the multiplicative identity of A, are continuous maps. Okay, what is a continuous map? Okay, a continuous map is a continuous function. Okay, they are the same thing with respect to the topology of the space. Okay, next, problem 26. What is a topological space? Okay, topological space had appeared in the solution to the previous problem. Okay, that is problem 25. Okay, solution. Okay, first let us see the definitions of the topological space. The utility of the notion of a topology, okay, is shown by the fact that there are several equivalent definitions of this structure. Okay, here notion means the concept. Okay, thus one chooses the axiomatization Okay, we will explain what is the axiomatization later. Suited for the application, the most commonly used is that in terms of open sets. Okay, what is an open set? Okay, let us search. Okay, open set. Open set. Okay, we have introduced what is an open set in problem 8. If you forget what is an open set, please review the solution to problem 8. Okay, let us go to the problem set we have seen before. Oh, sorry, problem set, open sets. Okay, here. But perhaps more intuitive is that in terms of neighborhoods, and so this is given first. Okay, due to the time limitation, I only list the definition via neighborhoods here. Okay, if you want to know other definitions such as definition via open sets or the definition via closed set, okay, you can refer to this reference. Okay, let us go to the end of this solution. Okay, you can refer to reference 125. Okay, topological space. Okay, let us go back to the definition via, oh sorry, not this, via neighborhoods. Okay, this axiomatization, okay, is due to Felix Hausdorff. Okay, who is Felix Hausdorff? Okay, he is a man, and we will introduce who is he later. Okay, let X be a set, and the elements of X are usually called points, though they can be any mathematical object. Okay, we allow X to be empty. This sentence means that X can be empty or can be non-empty. Okay, this is the meaning. Okay, let n be a function assigning to each x point in X a non-empty collection n of x. Okay, n of small x of subsets of capital X. Okay, the elements of n of small x will be called neighborhoods of small x with respect to n, okay, or simply neighborhoods of X. The function n is called a neighborhood topology. Okay, we will explain what is the neighborhood topology. Okay, later. Okay, if the axioms below are satisfied, and then X with n is called a topological space. Okay, let us see the following axioms. Okay, the first axiom is if n is a neighborhood of X, okay, that is n is in n of X. Okay. Okay, in order to distinguish this capital N and this capital N, okay, we will call this capital N the KL_N. Okay, what does this mean? Okay, let us show you KL_N. Okay, like this. Okay, KL_N. Oh, sorry. Here. Okay, then X is in N. Okay. In other words, okay, it is 25 minutes. Let us take a break.